We're going to look at addition, subtraction, multiplication, and division with whole numbers. And that means we'll be looking at both base 10 numbers and we'll be looking at numbers in other number bases. But we will start with base 10. So just a reminder that when we are looking at a number that's written in a particular number base, that means we're considering place value. And place value would mean that we are grouping together all of these objects in groups according to the number base. So in base 10, we're grouping together as many groups of 10 as we can at a time. And in this case, since we have one group of 10 and 4 ones left over, that would be the number 14 in base 10. The 1 means one group of 10, and the 4 is the 4 ones that we could not group together. So if we're going to look at some algorithms for addition, we might want to think about how we could represent a problem like 15 plus 16 using a very concrete representation. So we might represent these numbers using base 10 blocks. So literally the number 15 could be represented as one group of 10 with 10 grouped blocks and 5 ones with 5 ungrouped blocks. And 16 could be represented with one group of 10 and 6 ones left over. Now to add these together, you can think about that set model we have for addition. Adding these two sets of blocks simply means putting them together. And when we do that, the ones can be regrouped because we do have at least 10 ones. In fact, since we have 11 ones, we had 5 ones plus 6 more ones, we can group 10 of them together with one left over. Now if you look at how many groups of 10 we have, there's 3 groups of 10 with one left over, which is why 15 plus 16 is equal to the number 31. 31 means 3 groups of 10 with 1 1. Now we can take that same notion and look at it in a more abstract method with the expanded algorithm. If we're adding 15 plus 16, we can look at the digits that we have in the ones column and say that we have 5 ones plus 6 ones, which would give us 11 ones. Then we can look at the digits in the tens column and recognize that each of those ones in the tens column represent one group of tens. So we have one group of 10 in the 15 and one group of 10 in the 16, which is 2 groups of 10 or 20. So now we have 11 plus 20, which is 31. Now the traditional algorithm is probably what you are used to doing. You're probably used to saying something like 5 plus 6 is 11, and then you have to take that 11 and pull it apart as one 10 and one 1. The 1 1 you write in your ones column, and the 1 10 you write in your tens column. You may have used the word carry when you learned how to do this, and that's not a horrible word to use, but you might want to use the word regroup. So we're adding the 5 ones and the 6 ones. That gives us 11 ones, so we regroup 10 of those 11 ones and call that a 10, and then one of those ones we can't regroup, so it is going to remain in our ones column. So now if we look at the tens column, we have 110 plus 110 plus 110, which is 3 tens. That's the 30 in 31. Now there's another method for addition that might not be familiar to you. It's called scratch addition. And scratch addition is a way of adding numbers together that allows us to recognize that when we add these numbers together and we have enough to group according to the number base that we're working with, that we could do that regrouping as we add and then continue on with our addition. So here's what I mean by that. You might well look at something like this and say, well, let's see, I'm going to add in the ones column. So let's see, 3 plus 6 is 9, and 9 plus 4 is 13, and 13 plus 9 is, okay, numbers are getting a little bit big now. So let's see how we can do some regrouping along the way so that we don't have to work with numbers that are quite so big. We're still going to start with the ones column. So we're going to start by saying 3 plus 6 is 9. I don't have enough to regroup in 9, so I'll say that 9 plus the 4 is 13. Now 13 represents a group of 10 and 3 ones. So we'll make a scratch to represent the group of 10, and we'll write down the 3 ones. You can almost see the number 13 in that if you think of that scratch as being like the 1 in the number 13. Now we're going to leave that scratch where it is. That's our group of 10, but we're going to take the ones, which is that little 3 we just wrote down, and continue adding that to some other ones. So 3 ones plus the 9 ones underneath it is 12 ones, which is one group of 10 and 2 ones. Now we're done adding everything in the ones column, so those 2 ones are ungrouped. But if we look above that, we can see 2 scratches. That's 2 groups of 10 that we were able to regroup while we were doing the addition. We're going to take those 2 groups of 10 and we're going to move them to the tens column so that we can combine them with groups that are the same size. So now let's look at the tens column. We have 2 plus 1 is 3. That's not enough to group. Now it's 3 tens we're adding. 2 plus 1 is 3 tens, and then 3 plus 2 would be 5 tens, and then 5 plus 6 would be 11 tens. Okay, so now I can do some regrouping. I have 11 tens. I'll group 10 of those together and leave one of those tens ungrouped. And then 1 plus 3, 1 10 plus 3 tens is 4 tens. Now if I look up in that column, I'll see that I did have one group, that's the one scratch over the 6, one group of 10 tens, which is actually a 100. So the numbers add up to 142. Let's try that one more time. Let's add these numbers together. Now we're going to start in the ones. 8 ones plus 7 ones is 15 ones. That's a 10 and 5 ones. 5 ones plus 3 ones is 8 ones. That's not enough to group. 8 plus 9 is 17 ones. That's a 10 and 7 ones. Now those 7 ones can't group with anything, but if I look in the column above that, I can see that I did group twice. So I'm going to take those 2 groups of 10 and organize them in the tens column so that I can combine them with other groups of 10. So now we're in the tens column. 2 tens plus 7 tens, that's 9 tens. 9 plus 9, that's 18 in the tens column, so that's a group of 10 and 8 ones. 8 plus 8 is 16. That's a group of 10 and 6 ones. 6 plus 7 is 13. That's a group of 1 and a group of 10, excuse me, and 3 ones. Now every time we say a group of 10 here, we're actually doing a group of 10 tens. And we ended up with 3 ungrouped tens. Notice how that 3 is in the tens column. And how many did we have grouped up above that? Well, look at the scratches. I see 1, 2, 3 scratches in that column. That's 3 groups of 10 tens. That's 3 hundreds. So that 3 is going to move to the hundreds column so it can combine with the other groups of 100. So here we go in the hundreds column. 3 plus 4 is 7. That's 7 hundreds. 7 plus 5, that's 7 hundreds plus 5 hundreds. 7 plus 5 is 12. 12 hundreds, so we're going to group 10 of those together and leave 2 ungrouped. 2 plus 9 is 11. It's actually 11 hundreds. 11 is a group of 10 with 1 ungrouped hundred. And then 1 plus 6 is 7. And now if we look up above that in the column, we can see there were 2 scratches. That represents 2 groups of 100 that were grouped into 10 at a time. In other words, two 1,000s. So that gives us the number 2,737. So we're used to base 10. We're really comfortable with it because we've been doing it for many, many years. Let's see what base 4 addition is like. Now remember that in base 4, there's only 4 allowable digits, 0, 1, 2, and 3. So if we wanted to make a base 4 addition table, it would look like this. We would see what do we get when we add the digits 0, 1, 2, 3 with the digits 0, 1, 2, and 3. So let's complete this table and think about what's happening as we add these digits. So I'm going to start in the first row. We have 0 plus 0, well that's still 0. 0 plus 1 is still 1. 0 plus 2 is still 2, and 0 plus 3 is still 3. So nothing unusual there. Go to the second row. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. And here's where you have to be careful. 1 plus 3 to us in base 10 is 4. But in the base 4 world, there is no digit 4. In fact, once you get to what we know of as 4 in base 10, in base 4, there's some regrouping that goes on. 4 in base 10 is the same thing as one group of 4 and no 1s in base 4. So 1 plus 3 is 1, 0 in base 4. Let's go to the third row. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2, now go ahead and let yourself think in base 10, but then you have to write in base 4. So 2 plus 2 is 4 to us, but in base 4, that's 1, 0. 2 plus 3, well that's 5 to us, but in base 10, that would be a group of 4 and 1, 1. So 2 plus 3 in base 4 is 1, 1. Last row. 3 plus 0 is 3. 3 plus 1. Now I'm thinking 4 in my base 10 brain, but I know that 4 in base 10 is 1, 0 in base 4. 3 plus 2, I'm thinking 5 in base 10, but that's actually 1, 1 in base 3, or base 4, excuse me. And 3 plus 3, now I'm thinking 6, but I know that that's a base 10 number that's not in base 4. So 6 in base 10 is the same thing as one group of 4 and 2 1s. So that's actually 1, 2. So we've got this base 4 addition table, and if we wanted to do base 4 addition problems, we could use this base 4 addition table. Although you're probably not going to want to build an addition table every time you want to do an addition problem in another number base, but all that work you see on the right side with changing a base 10 number to a base 4 number, that's the sort of thing you're probably going to be doing a lot of when you do addition in other number bases, because you're going to be thinking in base 10, because we do have a base 10 brain, but then you'll be writing in base 4, or base 5, or base 7, or whatever the base is. So let's see if we can add 2, 3 base 4 plus 3, 2 base 4. Remember, we don't want to call those 23 or 32 because that implies that these are base 10 numbers, and they're not. They're base 4 numbers. So if we use a traditional algorithm, we could say, all right, if I look in the ones column, I have 3 1s plus 2 1s. And you could use your base 4 addition table and notice that 3 plus 2 is 1, 1. That's one group of 4 and 1, 1 left over. So that 1, 1 we could write in the ones column, and that one group of 4 we would write in the fours column. So now let's add in the fours column. 1 plus 2 is 3. 3 plus 3 is, okay, my base 10 brain tells me 3 plus 3 is 6. But 3 plus 3 I know is 6 in base 10, but 6 in base 10 is not 6 in base 4. It's actually 1, 2 in base 4. It's one group of 4 and 2 1s. So 2, 3 base 4 plus 3, 2 base 4 is 1, 2, 1 base 4. Let's try another base 4 addition problem. So we start with the ones column. 3 plus 3, you can use the table. and see that 3 plus 3 is 1, 2. Or you could say, okay, 3 plus 3, I'm thinking 6 in base 10, but 6 in base 10 is actually a 4 and 2 ones. So there's my 2 ones, and there's my group of 4. 1 plus 0 plus 3, in base 10 that would be 4, but in base 4, 4 is actually 1, 0. So there's the 0, and there's the group of 1 group of 4. And then in the we're not in the 4s column anymore, we're in the 4 squareds column. This is the 16s column to us. 1 plus 2 plus 1, I'm thinking 4 in base 10, but it's in base 10. I'm letting myself think. I want to write in base 4. So 4 in base 10 is 1, 0 in base 4. So the sum of these two numbers is 1002 base 4. So we can do this addition in any number base. We simply have to think about what's going to happen when we add the digits together, and do we have enough to regroup. So if we're in base 5, we have to remember that the allowable digits in base 5 are only 0, 1, 2, 3, and 4. So when we add 3 plus 4 in base 5 and get 7, which is a base 10 number, we can't write 7. 7 is not an allowable base 5 number. But we could rewrite 7 in base 10 as 1, 2 in base 5. It's 1, 5 and 2 ones. Now the 2 ones we'll write in the 1s column. The 1, 5 we will regroup into the 5s column. And now in that 5s column we have 1 plus 2 plus 1. 1 plus 2 is 3, 3 plus 1 is 4, and 4 is an allowable digit in base 5. We don't have enough to regroup if we only have 4 of something in base 5. So our sum is 4, 2, base 5. How about base 8? So now we have to think about grouping by 8s. I'm going to start with the 1s column. 5 plus 7, I'm thinking 12. That's a base 10 number though. 12 in base 10, if I'm going to group by 8s, would be one group of 8 and 4 ones. So to write this as a base 4 number, I'm going to have to write down the 4 ungrouped ones and then regroup those that one group of 8 into the 8s column. So now we're going to add in the 8s column. That's 1 plus 7 plus 2. Let's see, 1 plus 7 is 8, plus 2 is 10. Do you notice how I'm letting myself think in base 10, but I have to write in base 8. So 1 plus 7 is 8, plus 2 is 10. 10 is not a base 8 number. In fact, in base 8, 10 is one group of 8 and 2 ones. So I'll write down the 2 ones. It's really 2 8s because we're in the 8s column. And I will take the regrouped 1 and put that in the next column, which is actually the 8 squareds column, the 64s. So now let's add in the last column. 1 plus 2 is 3. 3 plus 3 is 6. 6 is a small enough number that we don't have enough to regroup in base 8. So the sum is 6, 2, 4, base 8. Now remember, base 12 is really no different than the other number bases. We're just grouping by 12s. We just have these strange symbols. We know that T means 10 and E means 11. Otherwise, addition is really no different in base 12 than it is in any other number base. So I'm going to allow myself to think in base 10, but I'm going to write in base 12. So I'm going to think 9 plus 5 is 14. That's a base 10 number. Now if I regroup that 12 at a time, I can get one group of 12 and 2 ones out of that. So the 2 ones I'll write in my ones column, and that regrouped group of 12 I will put in the 12s column. So now in the next column I have 1 plus T plus 7. T is 10, remember, so 1 plus 10 is 11. 11 plus 7 is 18. That's a base 10 number. I have to regroup that by 12s. 18 is a group of 12 with 6 left over. So my sum is 1, 6, 2, base 12. So let's talk a little bit about subtraction. Subtraction, if you think of it as takeaway, you'll be able to see what's going on when we're looking at these numbers in terms of their place value. So let's look at a base 10 number first. If we have 32 minus 15, and we look at that in a very concrete way with base 10 blocks, we would start with 32 blocks. And then we want to take away 15. Now 15 means we're trying to take away one group of 10 and we're trying to take away 5 groups or 5 ones. And we don't have 5 ones represented here. So what we'll have to do is some regrouping. We'll have to take one of those groups of 10 and we'll have to regroup it. In other words, break it up into the 10 ones that it's equal to. That leaves us with 2 groups of 10. And we have enough ones now that we can take away those 5 groups of 1. So we'll take away 5 groups of 1 and we'll take away 1 group of 10. That's taking away 15. And what we have left is 1 group of 10 and 7 ones, so our difference is 17. Now the traditional algorithm actually does exactly what we just saw. We always start with the ones column, and in this case we would be saying I'm trying to subtract 5 from 2. Now be real careful here. Don't say you can't subtract 5 from 2, because you really can. If you subtract 5 from 2, you get -3. But remember, we're dealing with whole numbers here, so we are not looking at the world of negative numbers at this point. So saying you can't subtract 5 from 2 is mathematically incorrect. What you could say is, I can't take 5 ones away from 2 ones. So I'm going to do some regrouping. I'm going to take one of those 3 tens and I'm going to regroup it. That would leave me with 2 tens. Now the 10 that I'm regrouping, I'm going to break up into 10 ones. Those 10 ones will add to the 2 ones and give me 12 ones. And that's probably the way you're used to writing it, with a little 1 up there. Think about what that really means. That means that 1 10 broke up into 10 ones, and now you have 12 ones. If you have 12 ones, you can certainly take away 5 ones from that and get 7. And then if you have 2 tens, you can take away 1 10 from that, and that would leave you with 17. Now, if we're dealing with numbers in other number bases, exactly the same thing is going to happen, but you have to keep place value in mind. Plus, we're going to make one very slight concession to our base 10 brains that will allow us to do this subtraction without making too many mistakes. So let's say we want to take 3 2 base 4 and take away from that 1 3 base 4. If I start in the ones column, I'm trying to take away 3 ones from 2 ones. I need more ones in order to do that. So what I'm going to do is some regrouping. I'm going to have to take one of those groups of 4 and regroup it, break it up into ones. So if I take one of those 3 groups of 4 and I break it up into ones, that's going to leave me with 2 groups of 4. And now the question is, how many ones do I have? Well, if you take a look at the blocks, you'll see that we have 6 ones. Now, how are we going to deal with that when we're just writing this down with numbers? Well, we're going to say we took one of those groups of 4 away. We broke it up into 4. And we added that to the 2 ones we had already, and here's the concession to your base 10 brain. That gives us 6 ones. Now a base 4 person does not know what the number 6 is. We're writing that number up there because we can think in base 10 very easily to subtract. So when we look at this, we say, oh yeah, that's 6 ones. A base 4 person would call that 1 2 ones. But if you call it that, you're going to think it's 12 and you're going to make mistakes. So go ahead and say, that's 6 1 ones. So 6 minus 3 is 3. and 2 minus 1 is 1. So if we take away the 1 group of 4 and the 3 ones, we are left with 1 group of 4 and 3 ones. So let's try one more subtraction problem where we are going to use blocks. This is base 7. So we have 526 base 7 minus 461 base 7. Now the 526 base 7 means we're starting with 5 groups of 7 sevens. Those would be 49s to us. 2 groups of 7 and 6 ones. So that's 526 base 7 represented with base 7 blocks. We're trying to take away from that 461 base 7. So if we start with our smallest units, that would be the ones. We're trying to take 1 from 6, and we can certainly do that. We can take away 1. But if we go to the sevens, we're trying to take 6 sevens away from 2 sevens, and we don't have enough sevens to do that. So we're going to have to do some regrouping. We're going to have to take 1 of the 7 sevens, 1 of the 49s, and regroup it. So if we take 1 of the 49s, that will leave us with 4 of them. And when we take that 1 group of 49 and break it up into sevens, we have 7 of those sevens, plus the 2 that we had already. 7 plus 2 is 9. Now remember, 9 is a base 10 number, but that's okay. We can think in base 10. We just have to write our final answer in base 7. So 9 minus 6 is 3 left. And then we're in the 7 sevens column, the 49 columns. We have 4 of those 49s. We want to take all 4 of them away. And what do we have left? We have 3 groups of 7 and 5 ones left. Take a look at the blocks. You'll see that's exactly what we have. 3, 5, base 7. So let's try a base 12 problem. And this one we're going to do without the blocks. If I want to start with the ones column, I'm trying to take 8 ones from 3 ones. I need some more ones in order to do that. So I'm going to go to the next column, which is actually my 12s column. And I see that I have 5 of those 12s. I'll take 1 away and I'm going to break it up into 12 pieces, 12 ones, that will combine with the 3 ones I have already and give me 15 ones. So now I think I'm in business. In my ones column, I've got 15 minus 8, which is 7. In my next column, which is actually my 12s column, I have 4 minus 2, which is 2. And in my third column, which is actually my 144s, I have 10, that's what T is, minus 5, which is 5. So my difference is 5, 2, 7, base 12. So now we're going to shift gears a little bit and talk about whole number multiplication and division. And we're going to start by just talking about a little bit of terminology. So if we have this, 3 times 5 equals 15, the numbers that we're multiplying are called factors, and the result of that multiplication is called the product. We do have some models we can use for whole number multiplication. And we're going to use the 3 times 5 equals 15 as our example for these models. There's something called a repeated addition model, and that simply recognizes that multiplication is nothing more than addition done over and over again. So when we have 3 times 5 equals 15, we can think of that as saying we have 3 5s, 3 times 5. So 3 5s would be 5 plus 5 plus 5, which also equals 15. The repeated addition would be the 3 5s that we're adding together. So here's a released item from the 2004 MAP test for 4th grade. The problem says to look at this array of stamps and first of all to write a multiplication number sentence to find out how many stamps are on the sheet. So that might be something like 4 times 5 equals 20 or 5 times 4 equals 20. And then a On the bottom line, it says write an addition number sentence to find out how many stamps are on the sheet. So that might be something like 5 plus 5 plus 5 plus 5 equals 20. So what we're looking for here is that relationship between multiplication and addition. So we'll look at some other models for whole number multiplication. There's something called an array model, which is also sometimes called a grid model. And here's how that works. If we're multiplying 3 times 5, we're going to draw 3 lines in one direction and 5 lines in the other direction. And then what we're going to be looking for are the intersections of the lines. So we'll count all the intersections that we have. And if we count the intersections, we'll find out that the number of intersections is the same thing as the product. So since there's 15 intersections, 3 times 5 is 15. There's an area model for whole number multiplication, which can look kind of similar to the grid model, but we're going to be counting different things. For the area model, we start with a rectangle, and then we divide the rectangle up into pieces. In this case, since we're multiplying 3 times 5, we divide it into 5 pieces one direction and 3 pieces the other direction, and then what we count is the number of rectangles inside the large rectangle. Since there's 15 rectangles inside the large rectangle, we know that there's 15 that we have a product of 15 for our multiplication problem 3 times 5. There's a little bit of other terminology we're going to talk about. The first is the idea of closure. A set is closed under multiplication if the product of any two numbers in the set is still in the set. So for example, if we have this set, 1, 2, 3, 4, these are the counting numbers, and we want to know if it's closed under multiplication, what we're really asking is if we add any two numbers in this set together, do we always get something that's in the set? If we add any two counting numbers, do we always get another counting number? And the answer to that is yes. So this would be a closed set under multiplication. How about this set? It just contains 0 and 1. Now if we multiply any number in the set times any other number in the set, and that includes multiplying a number times itself, do we always get a number that's still in the set? So let's see, if we multiply 0 times 0, that's 0 and that's still in the set. How about 0 times 1? That's still in the set. How about 1 times 1? Well, that's 1, that's still in this set. So this one would be closed under multiplication. How about this set? It contains 0, 1, and 2. Can we multiply any number inside this set times any other number inside this set, including multiplying a number times itself, and get something inside the set? And in this case, we can't. And the problem is, if we multiply 2 times 2, we get 4, and 4 is outside of this set, so it would be considered not closed under multiplication. There's some properties of whole number multiplication that will look similar to the properties of whole number addition. There is a commutative property of multiplication that says that we can multiply numbers in any order and still get the same product. There's an associative property of multiplication that says we can group numbers that are being multiplied in any way and still get the same product. There's an identity property of multiplication that says there is a number we can multiply any number by and get the same number we started with. And that number is the number 1, which makes 1 the multiplicative identity. And then there's a property that's unique to multiplication, which is the zero multiplication property. The zero multiplication property simply says you can multiply any number times 0 and you'll get 0. The distributive property combines multiplication and addition, and its actual name is the distributive property of multiplication over addition. This is a property you are no doubt really familiar with in algebra, but you may not be familiar with how to show the distributive property using a model. So we're going to use a rectangle model to illustrate 3 times the quantity 4 plus 1 equals 3 times 4 plus 3 times 1. So here's how we can do that. The rectangle is going to show 3 on one side and 4 plus 1 on the other side. So here's how we'll show that that's 4 plus 1. We'll actually divide this rectangle into 4 columns on one side and 1 column on the other. Now that illustrates the left side of that equation. The right side, what we're going to imagine is that on that dark line, we're going to just cut this rectangle right down that dark line and then pull it apart. And if we do that, we're going to get this rectangle and this rectangle. We get a rectangle that's 3 by 4, and we get one that's 3 by 1. And if you look at the right side of the equation, you'll see that's exactly what it's saying. 3 times 4 plus 3 times 1. So that's some models for addition, subtraction, multiplication, and division, and working with some of the numbers in base 10 and other number bases using those same operations.